Okay, so today we'll start another topic. So we studied area vector and electric flux. Today let us start Gauss theorem. Gauss theorem. This theorem is quite important and it is used extensively in electrostatics. You will find its use many times, right? So let us see what it is. There is a scientist named Gauss. He gave a theorem which is known as Gauss theorem. Now this theorem gives the relationship between electric flux. All right.
Yeah.
And
are you sharing your screen?
oh, let me see. Can you see?
I don't know. But I can see it in the link you sent me.
No, that's not the.
Also, in the link, I cannot see the notes of that.
Hmm. This Gauss theorem gives the relationship between the total flux passing through any closed surface and the net charge enclosed in the surface. Electric flux and net charge inside the surface. Okay, so let us first write what is the statement of this theorem. So it is written that the total flux through a closed surface right, it is equal to 1 by epsilon naught times the charge enclosed by the surface. Well, let us see what does that mean. For example, you have a surface. This is some surface, okay, and inside this surface there is some charge q. All right. Now due to this charge there will be some electric field, and due to that electric field this surface would be having some flux, isn't it? Like this way electric field will go from a point charge, spherically symmetric. So this surface is cutting the electric field, right? There will be some flux. Now this theorem gives that flux directly. Okay, so what does it say? That this flux phi, which will be passing through this surface, will be equal to 1 by epsilon naught times the charge inside this surface. Alright, so there is no need to calculate the electric field E and then find the flux using E dot ds, right?
Yeah.
This is the usual definition of flux. Flux is the surface integral of E dot ds, right? This is the dot product, right? But here, by using the Gauss theorem, if you are given some charge inside the surface, right, so you can directly find the flux through that surface by multiplying that charge with 1 by epsilon naught. Okay, so in other words, you can equate all of these three equations like this. Flux through a surface is given by integral for the surface S E dot ds, which is also equal to, it can be written as q by epsilon naught, right?
Yeah.
So this is final result that we have. Okay,
Okay.
now let us prove this result, that flux is equal to q by epsilon naught, or 1 by epsilon naught times. From now onwards I will call it as q by epsilon naught, not 1 by epsilon naught times of q. Alright, because that's the same thing. Now let us prove this Gauss theorem. Proof, very simple proof. Alright, for the proof we will assume something. First of all, we will assume charge q, okay, situated at some inside a surface. Now what we do is, there is this spherical surface around that charge. All right,
Yeah.
this is a spherical surface around this charge, and this charge is situated at the center of this sphere or spherical surface. So you can say that this distance will be the same from the center to the radius, to the circumference.
Yeah.
Now what we do is, we assume, because this surface hole is S, we can assume a small surface ds
Yeah.
is ds, right? And this ds direction will be outwards. All right.
Yeah.
Now another thing is that due to this charge q, there will be electric field, isn't it? This charge will
Yes.
generate
Yeah.
electric field. Now if we talk about the electric field on the surface, just on the surface, right, so the electric field would be directed outwards,
Yeah.
isn't it? If you even take some other point, the electric field would be outwards, like this, right?
Yeah.
And you take the similarly some small ds surface, so it would be pointing outwards. The thing I want to say is that both the ds and e are pointing in the same direction. All right, so here this is this electric field. Now by normal inspection, what we can say about the electric due to this charge, 1 by 4 pi epsilon naught q by this r radius square,
Oh yeah.
and the direction would be outward, radially outward, correct?
Yeah.
Now this field point radially outward at all points, you know, so this is the electric field at all points on the surface, the circumference, isn't it? Because the radius is same and all of these are constant. Q is already fixed, 1 by 4 pi epsilon naught is also a constant. and r is also fixed in this on this surface, right?
Yeah.
So this will be the electric field at all points on the surface, isn't it?
Yeah.
So we can say that, we can just say that on the surface S, electric field is constant, isn't it?
Yeah.
Now first note this thing, that electric field on the surface is constant. Alright. Now the second thing to note is that any area element point radially outwards also, which is in the direction of E. Right?
Any what?
Any ds, right?
Yeah.
Any small area vector, because I told you, suppose this is a small area ds, the normal unit vector to it would be in the direction like this, perpendicular to it, isn't it?
Yeah.
Same case here, these small ds, okay,
Yeah.
all of them unit vector, area vector would be outwards,
Yeah.
and which would be in the same direction as the electric field at that point, isn't it? The
Yeah.
electric field at this point would also be in the same direction outward. All
Yeah.
right. So this is the first thing. Now we will use this theorem, the flux formula. So what is small d phi? It is E dot ds,
Integral.
right?
Yeah.
I'm talking about the small one, not the, this is the full phi, okay? The small phi, small flux due to the small surface, isn't it?
Yeah.
That would be d phi is equal to d dot, because phi is generally what, E dot s, and this if is small then it will be ds, right?
Yeah.
So here it comes from, so d phi is E dot ds. Now if you want to find d phi for suppose, let's say one of these, let's say at this point we want to find d phi, okay? So what would
Yeah.
be d phi? E dot ds, or in we can say E into what, into ds into cos theta,
Oh, okay.
and for every ds the theta angle is 0, isn't it?
Yeah.
Theta is 0 between E and ds at any point on the surface, at any point.
Yeah.
So in effectively you can say this is cos 0, which is 1. So d
Yeah,
phi would become E into ds.
Yeah.
This is the small flux, right?
Yeah.
D phi due to the small surface. Now what is the total flux? So total flux is given by, if you take the integral of this, isn't it? So total flux is given by integral of d phi, all right?
Yeah.
That means adding up all the small fluxes produced by each one of the d phi's, and that
Yeah.
is given by, so d phi can be replaced by E ds, right? From this
Yeah,
equation.
Yes.
So in place of d phi you can write E ds here, correct?
Yeah.
Now see, this is actually, this is a closed integral over the surface, okay? So I told you the constants are taken outside the integral, did I?
Yeah.
This is a normal thing to evaluate an integral, okay? The constants are taken outside, and the ones which are variables, which are then integrated and then solved. Although I have not told you how to integrate, but I told you that we take out the constant, right? So can you say which one of them is a constant here on the surface S? E is a constant, you know.
Yeah.
I proved it to you that E is this at any point on this surface.
Yeah.
And because since we are talking of this surface integral, so E is constant for that. So E can be taken out, and then inside we will have the surface integral of ds. Okay. And you know what? There is some interesting point to make here. When you add all of these small ds, because integration means to add up, right? To add up continuous things. So when you add each one of these small ds, okay, when you add each one of these small ds,
Yes. Yes.
what you will get is, whenever you do this thing, you get the area of that surface.
Oh, so 2 pi r squared.
Yeah. So since this is what? This is a sphere. Remember, this is not a circle. Q is a charge situated and it will emanate spherically, right? Electric field would be emanated spherically. So the area that would be accounted here for is the sphere, not the circle. So this is a sphere. And what is the area of a sphere? 4 pi r square. Alright?
Yeah.
So you should remember this thing. Whenever we do a surface integral over a surface, that gives the area of that surface.
Okay.
Okay? Because you add each one of those individual ds and adds up, right, to give the total area.
Okay.
Okay, so on this side we had total flux, which is phi, and what we have got is E into 4 pi r square, isn't it?
Yeah. Yes.
So this is what we have got for phi. Now what we need to prove is phi is q by epsilon naught, right?
Yeah.
How do we do that?
Like you substitute E with
Yeah, very good. So we will substitute the value of E which we found earlier. Okay. In fact, you can find its magnitude also. Then there will be no vector here, right? So E magnitude is 1 by 4 pi epsilon naught q by r square. So let's just do that. 1 by 4 pi epsilon naught q by r square into 4 pi r square. Alright.
so 4 pi r squared looks good.
4 pi r square get cancelled, and what we are left with, phi is equal to q by epsilon.
Right. So hence proof.
Yes, this is the proof of Gauss theorem.
Okay. That was pretty simple.
Okay, just wait, I'm getting a call.
Okay.
Hello? Hello? जी वालेकुम अस्सलाम. So it comes quite handy to find the flux when it is difficult to find the electric field, you know, because flux is what? Surface integral of E dot ds, and now it can also be written as q by epsilon naught.
Yeah.
There are two ways to find flux. Either you find it using the electric field, like the flux formula, the original one, or either you do it by the Gauss law, Gauss theorem. So whenever sometimes it is difficult to find the flux using this formula, right? Then we can use this, the Gauss theorem. Let us do a question. Okay, so let us do a question. Let me. This is the question.
Yeah.
So what it is that a cylinder is placed in a uniform electric field E with its axis parallel to the field. You know what the axis is? Suppose this is a cylinder. This is called the axis of the cylinder, right?
Sure.
So the axis is parallel to the field. Let's say this is the field. Uniform electric field is given, right? So we can draw like this. And now a cylinder is there, so it is placed inside this electric field and the axis is parallel to the field. That means like this a cylinder would be placed.
Yeah.
Okay, we need to find, or we need to show that the total electric flux through the cylinder is 0. Oh, so you should remember that the cylinder is a 3D object first.
Yeah.
Right, it is not a 2D
I don't
object.
remember the
So
area for.
I'll tell you. First thing first, that it has having 3 surfaces, 1, 2 and 3. So how come
The
this
two
is the
circles
first one,
and
the
second
circle on
piece.
the left hand side, and the
Right.
whole curved surface area that we call, right? That the curved one is the second one, and the another circle on the right hand side is the third circle, right? It has got 3 surfaces. So we need to find the total electric flux. That means we need to find the flux through each one of these surfaces and add them, right?
Yeah.
So that would be the answer. So how do we do that? We can use flux phi equal to the integral E dot ds,
Yeah.
and I'm keeping the symbol as in this circle that is interchangeably used, right? So don't mind that. Flux is integral of E dot ds. Now how do we do that? First, see, the electric field is constant, right? So if you talk of this surface, the electric field is in this direction, but the area vector ds would be in this direction, right?
Yeah.
So in the first case, the theta between E and ds would be 180 degrees,
Yeah.
correct? Now what we can do is flux for first surface we are calculating, and integral of E dot ds. So integral of E into ds into cos 180,
Yeah.
correct? Cos 180 is how much? -1, right? Cos 0 is 1, but cos 180 is -1. So that would be minus E ds integral. Okay, and the electric field constant everywhere, so the constants can be moved out. So minus E integral ds. All right.
Yeah. Yeah.
And what is this ds integral here? The area of the circle itself.
Yes. Yeah.
So minus E into ds, which is pi r squared.
Okay.
That is the flux through the first surface, correct?
Yeah.
Got the concept? Now
Yes.
flux through the second surface. So for this, you see that if we take this edge of the cylinder, right? This is a curved surface, and now electric field is gliding on it in this direction, but you can find easily that the ds would be pointing outwards at every point. See, this is a curved surface, right?
Yes.
So ds would be outwards, the unit area vector, isn't it?
Yeah.
It is similar to that of a circle. Suppose this is a circle.
Yeah.
or a sphere, so ds would be pointing outwards.
Yeah.
But this is a cylinder. Now
And it's
this
a curved
surface, this is
surface.
still a curved surface, you know. So
Yeah.
at every point ds would be outwards, and the electric field would be in this direction always. So in the second case, the theta between ds and E would be 90-degree, isn't it?
Okay. Yeah.
So now in this case, if you do E ds using this E dot ds, so E into
Yeah.
ds into cos theta, cos 90,
0.
it will take down everything to 0. No need to find anything
Yeah.
else. Phi for the third surface. Find the phi through the third surface. We have
So
this.
integral.
So this is E, and ds is also in this direction this time around.
Yeah, the same direction.
So the theta would be 0 degrees, right? Isn't it? So
Yeah.
E ds cos 0, cos 0 is 1, integral
1.
of E ds, and now we can take out E outside, and
Take
integral
out
of
cos
ds E into
which is
pi r
equals
square.
to, yeah.
Now these are the flux for each one of the surface. Phi
So
total
when you
would
add
be
them,
phi 1 plus phi 2 plus phi 3 minus e
it
pi
cancels
r
out.
square plus 0 plus e pi r square, which is, you can cancel it out, so it would be 0. The total flux through
0.
the surface, net flux, is 0, and hence proved. Okay,
Yeah.
this is how we do it. Now let us do some interesting problems related to finding the electric field. First thing is,
Okay.
you want to find field due to infinitely long charged wire.
Huh?
This is infinitely long, okay?
So it never ends.
What?
So like it will never end.
We are
Right, because it's a bit too long.
yeah, but that is the interesting part. Uh, this is the application of Gauss law, right? Or Gauss theorem. This is the application of Gauss theorem. There is an infinitely
Okay.
long wire, right? Let us first draw a wire. Suppose this is a wire. Cannot draw the infinitely long. We'll assume that it is infinitely long. So this is an infinitely long wire. Okay. And it
Yeah.
has a uniform charge density. So lambda is the uniform charge density, coulomb per meter. This wire is having a uniform charge density. You know what is charge density? Charge per unit length,
Charge per unit length. Okay.
isn't it? Which is lambda, linear charge density, because there is no, that is why we call it a lambda. That is
Yeah.
lambda coulomb per meter. So this is assumed to be infinite. Now what we will do is, we will assume a surface like this. This is the surface. Why I have left below, top and below, because that's infinitely long. Okay,
Yeah.
correct. This is the Gaussian surface that we have drawn around it.
Okay.
I'll tell you why did we draw only the cylinder Gaussian surface only. This thing we will study later on, because like it is drawn according to like we want to find the problem's answer in the most simplest way possible. So it would be not like practically possible to draw a haphazard surface, right? That would lead us to a infinite long answer as well. For
Yeah.
infinite long, that will study how to draw Gaussian surfaces. That is altogether a topic. But here what we have done is we have drawn a cylindrical Gaussian surface. That is, we have covered this wire inside a surface. That's it. One could have done it in a spherical way, right?
Yeah.
But these are the things that we'll study later on. Here what we did, when we were proving the Gauss theorem, here we did the spherical Gaussian surface. You could have asked why we have not assumed this charge inside a square or inside a cuboid, right? Like this, or inside a pyramid I have drawn. So this is the thing that we'll study later on. Because why did we draw this spherical? We wanted electric field to be in the direction of ds and constant everywhere. Only then this theorem is coming handy to us. Otherwise it is very difficult, no?
Yeah. Like in the end, it would cancel out with.
Yeah, we want to find symmetries in life.
Okay.
So here we also draw the Gaussian surface so that it is symmetrical, right?
Yeah.
Now we want to find the electric field due to this long charged wire. This has a uniform charge density lambda. So how do we do this? See, there are three surfaces here also, right? This is what you can say S1.
Yeah.
This is
I like the
S2.
cylinder. Okay.
Yeah, this S3. And if you see, like, what will be the electric field? What will be the
Zero.
electric field?
I'm sorry, not zero. I don't know, uniform?
Electric field due to this line charge, okay,
Oh,
it would be directed outwards like this.
okay, you're asking the direction.
Yeah, and everywhere on this surface it would be acting like this, right?
Yeah.
Let's draw one or two, don't draw many. So this is how the electric field will be. It will be radially outwards. And how would be this? This would be ds2. This would be ds3. And ds1 would be in the same direction,
Yeah.
isn't it? So for the first case, now let us find the total flux. Although we are finding the field, but we will find it with the help of flux. So what would be the total flux? Flux due to surface 1, flux due to surface 2, flux due to surface 3.
Flux through surface 3.
What would be the flux due to surface 1?
So,
Integral of E dot ds. So let us
integral.
first write the
Okay.
main formula. So this is what we use, right? E dot ds. So in the first case, the theta here would be what?
90.
90?
Oh,
0.
sorry. Wait. Yeah, sorry.
E is in the
Oops.
direction of ds,
I
right?
was looking at S2.
So E ds cos 0 plus flux
equals
due to
0.
S2. So for these E ds
It's
cos 90
cos 90.
plus flux due to 3 E ds
It's cos
90 again.
90.
Now these one will vanish straight away because cos 90 is 0, right?
Yeah, yeah.
Only this
So
one
we just have
remains. Phi is equal to E ds cos 0 is 1, right?
yeah.
Now
So E will get out.
on this surface, this was the first surface, right?
Yeah,
ds is the first surface here. So now on the first surface, like the curved surface area of the cylinder, this is the first surface, right?
yeah,
So on this curved surface, this r is fixed, right?
yeah.
So the electric field, which is kq by r square, will be
R
fixed
squared
due to
will be
this,
constant.
will be constant.
Yeah.
So take out this constant outside and write
So
ds.
E to
And what would be ds here? You tell me. ds would be the curved
uh,
surface area of the cylinder,
uh,
isn't it?
yeah.
And what is the curved surface area of cylinder? 2
Two
pi r
uh,
l.
uh,
Do you remember this?
wait, yeah, from 10th grade. What is L?
L is
And
the
N?
length.
Okay.
Okay, r is the length.
Yeah. R is the radius.
I'm sorry, this L is the length, this r is the radius.
Yeah.
And what is this length? The length of the cylinder, not the
Yeah.
wire, because wire is infinitely long. We don't know the length of it,
Yeah.
right? The length of the cylinder we have enclosed it in. This is what the
Uh-huh.
L is. Okay.
Yeah.
And another thing is that, so first thing you have found is E is equal to E into 2 pi r l. But you know what? Flux is also equal to Q by epsilon naught using Gauss theorem, right? Isn't it?
Yeah.
Flux is also equal to the Q divided by epsilon naught. What is that Q? The charge enclosed in the surface.
Charge. Yeah.
But how we will
So the
find the
charge on the
charge
wire?
enclosed in the surface? Yeah, wire itself. But it is not mentioned, right?
Now.
What we are given is, we are given the charge density, coulomb per meter. Okay, that means that for
Okay.
every meter length of this wire, we have lambda coulomb of charge, isn't it?
Yeah.
So for L length of the wire, how much charge would be enclosed in that wire? Lambda L, right?
Oh, lambda. Yeah.
So this Q can be replaced by lambda into L divided by epsilon naught. Are you getting it?
Yeah.
Because Q is not given, Q is given in the form of the densities. The charge density is
Yeah.
given. So given the length of this cylinder, we can find the charge inside that portion of wire. So this is lambda L divided by epsilon naught. Now this is the first equation, this is the second equation. You can equate two of them. Okay. So E into 2 pi r L is equal to lambda L on epsilon naught, and you can see L cancels out. Can you find E from here? Lambda upon 2 pi r epsilon naught.
Yeah.
This way you have found electric field at a distance r from infinitely long wire. You know what is this R?
Wire.
This R, right? uh, this R, right? So although this was infinite, we have been able to find the electric field at a distance R. Like, you know what is this distance R? Like the curved surface area of the cylinder.
Yeah.
So this is that E is equal to lambda upon 2. This is a very important result. You should remember this. Okay? You should remember this result itself. They will not be proving it. Neither they will ask you to prove. But it can come. It can be used to find some answer to some other problems.
Okay.
So this is one of the application of Gauss theorem. Without Gauss theorem, this would be quite elaborate exercise to find the electric field. Okay.
Yeah.
And the essence of the Gauss theorem lies in selecting this surface. How do you select this surface? Okay. So your expertise in determining this, whether you are getting it cylindrical or whether you are taking a spherical surface, because see, it is actually an imaginary thing, right? There is nothing like such. So that's the thing. Like, you need to master the art of finding this Gaussian surface. Although it won't be asked rigorously in exams, you would be asked uh, like the general questions from it, not new questions. Okay.